We've been searching for intelligent life in the universe for over 60 years. We've built massive radio telescopes, sent probes into the far reaches of our solar system, analyzed thousands of exoplanets orbiting distant stars, looked for technosignatures, biosignatures, any indication whatsoever that we're not alone in this vast cosmos. We've scanned the skies with increasingly sophisticated instruments, listening for patterns in radio waves that would betray the presence of another technological civilization. And we found nothing. Absolute silence. Not a single confirmed detection, not one verified signal, not even a hint or ambiguous whisper that another technological civilization exists anywhere in the observable universe. Before we dive into this topic, make sure to subscribe and comment where in the world you're watching from. I'm going to tell you something most scientists are reluctant to say publicly, something that goes against the optimistic narratives you hear in documentaries and popular science articles. It's not that we haven't found intelligent life yet, it's that it's impossible to find it. Not because the universe is necessarily empty, though it might be, but because of fundamental constraints imposed by physics, by biology, by the nature of intelligence itself, and by the brutal statistics of cosmic timescales. The depressing truth emerging from decades of research is that humanity might be the last intelligent civilization in the observable universe, perhaps the last one that will ever exist, and the probability that we'll ever encounter another technological species is essentially zero. That's a bold claim, and I need to back it up carefully because it goes against deeply held intuitions that have shaped thinking about extraterrestrial intelligence since the 1960s. So let me walk you through the arguments systematically, starting with the most famous equation in the search for extraterrestrial intelligence, the Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of detectable civilizations in our galaxy by multiplying together various factors: the rate of star formation, the fraction of stars with planets, the number of habitable zone planets per solar system, the fraction where life actually emerges, the fraction where life becomes intelligent, the fraction where intelligence develops technology capable of interstellar communication, and crucially, the length of time such civilizations remain detectable. When Drake first wrote this equation at the Green Bank Conference, the optimistic assumptions of the day led to estimates of thousands or even millions of communicating civilizations in the Milky Way alone, which generated tremendous excitement about the possibility of detecting alien signals and establishing contact. The equation seemed to promise that we lived in a galaxy teeming with intelligent life, and finding it was just a matter of building sensitive enough receivers and listening long enough. But as we've learned more about each term in the equation over the past 6 decades, as we've discovered exoplanets and studied the origin of life and understood evolutionary biology and cosmic history better, the estimates have plummeted. Every single term turns out to be much more constraining than early optimists thought. The probabilities are smaller, the requirements more stringent, the barriers higher. And when you multiply all these small probabilities together with our current best understanding, you get numbers close to 1 or less, meaning we might be alone in the galaxy, or at least so rare that detection is effectively impossible within any reasonable time frame. We now know that planets are common. The Kepler mission and other surveys have discovered thousands of exoplanets and shown that nearly every star has planets, and many have planets in the habitable zone where liquid water could exist on the surface. This sounds promising. There are billions of potentially habitable worlds in our galaxy alone. Surely some of them must have developed life and intelligence, right? But here's the first problem. Being in the habitable zone is necessary, but far from sufficient for life. The habitable zone is just a range of distances from a star where temperatures theoretically allow liquid water, but you need so much more than that. You also need the right atmosphere with the right atmospheric pressure and the right greenhouse gases in the right proportions. You need protection from radiation through magnetic fields and ozone layers. You need plate tectonics to recycle carbon and maintain stable climate over geological time. You need a large moon to stabilize axial tilt and prevent chaotic climate variations. You need the right orbital eccentricity and inclination. You need protection from asteroid impacts, ideally through gas giant planets in outer orbits that sweep up debris, and dozens of other factors that have to align correctly. Earth is not just in the habitable zone, it's the product of an extraordinarily specific sequence of events that might be extremely rare. The moon formed from a giant impact that was just the right size and angle to create a large satellite without destroying the planet. Jupiter and Saturn are positioned to deflect most comets and asteroids away from the inner solar system while still allowing some impacts that deliver water and organic compounds. Earth's magnetic field is generated by a liquid iron core kept hot by radioactive decay and tidal forces, and this field has persisted for billions of years, protecting the atmosphere from solar wind. The atmosphere has the right composition because of volcanic outgassing, photosynthesis, and chemical weathering, a delicate balance that could easily have gone wrong. Peter Ward and Donald Brownlee argued in their book Rare Earth that while simple microbial life might be common, complex multicellular life requires such specific conditions that Earth-like planets might be extraordinarily rare, perhaps unique in the galaxy or even in the observable universe. And while not all scientists agree with the most extreme versions of the rare Earth hypothesis, the basic point is well taken. Habitability is much more constrained than just being in the right temperature zone. When you calculate the probability that all these factors align, the number gets very small very quickly. The effective number of truly habitable planets might be orders of magnitude smaller, perhaps factors of millions or billions smaller than raw counts suggest. Even on truly habitable planets, life must somehow emerge from non-living chemistry. And here we hit another major constraint. We have exactly one example of life emerging, Earth, and we don't understand how it happened. We don't know what the specific chemical pathways were, what the environmental conditions required were, what the probability of the process is, or whether it's inevitable given the right conditions, or fantastically improbable. Life appeared on Earth very early, within the first few 100 million years after the planet cooled enough to have liquid water, which suggests maybe it's easy. Maybe life arises quickly whenever conditions are right, but we can't rule out the possibility that we were extraordinarily lucky, that the origin of life is so improbable it happens only once in billions or trillions of planets, and Earth just happened to be that one lucky planet. The chemistry is fiendishly complicated. You need to spontaneously generate self-replicating molecules, probably RNA or something similar, from simple organic compounds through random chemical reactions. But RNA is complex, requiring specific sequences of nucleotides that can fold into structures with catalytic activity. The probability of randomly assembling even a short functional RNA molecule is astronomically small. You need some kind of chemical evolution, some process that concentrates and organizes molecules and selects for useful sequences. But we don't know what that process is or whether it's likely to occur naturally. Lab experiments have shown that some building blocks of life, amino acids and nucleotides, can form under prebiotic conditions, but going from building blocks to self-replicating systems is an enormous leap we've never reproduced in the lab despite decades of trying. It's entirely possible that the origin of life is a 1 in a trillion event, that most habitable planets remain sterile forever, that Earth is the only place in the galaxy or even in the observable universe where life got started. This is called the Great Filter, a barrier so difficult to pass that it explains why we don't see evidence presence of aliens. One possibility is that the filter is behind us, that the origin of life is the hard step, and once you have life, everything else is relatively easy. If that's true, then even though there are billions of habitable planets, the number with life could be one or a handful or a few dozen, and the number with intelligent life could be effectively zero, except for us. Even assuming life is reasonably common, we still have to get from simple microbes to complex multicellular organisms and then to intelligence. Each transition might be extremely improbable. On Earth, life remained microbial for over 3 billion years. The evolution of eukaryotic cells with nuclei and complex internal structures, was probably a unique event, a one-time merger between different types of bacteria. This endosymbiotic event might be so improbable that it happens only once in billions of planets with life. Nick Lane has argued that the energy constraints on prokaryotic cells make it essentially impossible for them to evolve the complexity necessary for multicellularity. You need mitochondria to power complex cells. And even among planets with complex multicellular life, intelligence might be rare. Intelligence is not inevitable or the goal of evolution. It's just one survival strategy among many. Bacteria have been far more successful than humans by most metrics. Intelligence is energetically expensive, and for most organisms in most environments, the costs outweigh the benefits. Earth has had complex life for 600 million years, and only one lineage developed technological intelligence. One species out of millions or billions learned to make tools, fire, agriculture, and eventually radio telescopes. That's a success rate of basically zero. There's no reason to think other planets would do better. The galaxy is over 13 billion years old. The Sun and Earth are only 4.6 billion years old, which means the galaxy existed for over 8 billion years before our solar system even formed. Stars have been forming throughout that time, potentially creating habitable planets, some fraction of which might develop life and intelligence. So you might have had intelligent civilizations arising 5 billion years ago, or 8 billion years ago, or at any time in the galaxy's long history. And those civilizations might have lasted a few thousand years or a few million years before going extinct, transcending or disappearing in ways we can't understand. The point is this: even if intelligent life is not incredibly rare, even if there have been thousands or millions of intelligent species in the galaxy's history, they might never overlap in time. They might arise and disappear before other species develop. Ships passing in the cosmic night, never aware of each other's existence. And this is actually quite likely because the window during which a civilization is detectable might be extremely short. We've been capable of radio communication for only about 100 years. We've been broadcasting signals into space unintentionally through radio, television, and radar for only a century. And those signals are getting weaker as we switch to fiber optics, digital communications, and directed transmissions that don't leak into space as much. The era of loud radio broadcasts might last only a few centuries before civilizations either go extinct or advance to technologies that don't produce detectable signatures. And during that few century window, you're only detectable out to about 100 light years, the distance your signals have traveled, which is a tiny fraction of the galaxy, maybe 1/10,000th of the galactic volume. So at any given time, you're only visible to a tiny bubble of space around you. And unless another civilization happens to be within that bubble at the same time, looking in your direction with sensitive equipment, they'll never detect you. And the same applies to them. If there's another civilization 1,000 light years away, we can only detect them if they were broadcasting during the brief window when their signals are now reaching us, which might have been 1,000 years ago for them, and they might have gone silent or extinct long before their signals reach us. When you include temporal alignment in Drake equation calculations, the requirement that civilizations must exist simultaneously and within detection range, you get numbers that approach zero. Even if civilizations exist and broadcast, detection is effectively impossible for several reasons. First, the enormous energy requirement. Radio waves spread out as they travel. Their intensity decreases with the square of the distance. To send a signal detectable across thousands of light years requires gigawatts of power, broadcast continuously in all directions. This is an enormous investment with terrible return on investment. If you broadcast to a civilization 1,000 light years away and they respond, you won't receive their reply for 2,000 years total. Most civilizations probably don't intentionally broadcast because it's not worth the cost. Second, the search space is enormous. Billions of stars, an enormous range of radio frequencies, and we don't know what frequency aliens might use or what modulation schemes they might employ. SETI is like looking for a needle in a galaxy-sized haystack where the needle might not exist and might only be visible for brief moments. We've searched a tiny fraction of possible parameters. Third, as technology advances, civilizations become quieter. We're leaking less radiation into space using more efficient communications. If other civilizations follow the same trajectory, the window of detectability might be just a few decades, and catching a civilization during that brief window is vanishingly unlikely. Any civilization significantly more advanced than us would be so different that we might not recognize them as intelligent at all. Consider our trajectory. 1,000 years ago, no electricity. 100 years ago, no computers. 50 years ago, no internet. Extrapolating even a few centuries forward, human civilization will be unrecognizable. We might upload consciousness into computers, merge with AI, re-engineer our biology, colonize space in non-biological forms, or discover physics we can't currently imagine. A civilization 1,000,000 years older would be to us as we are to bacteria. Their technologies would appear magical, their presence invisible, because we don't know what to look for. This is the transcendence hypothesis. Sufficiently advanced civilizations inevitably transcend physical space, moving beyond conventional matter and energy into forms we can't detect. If this transition takes only a few thousand years, an eye blink in cosmic time, then almost all intelligent life exists in post-transcendence forms we can't perceive. The galaxy could be teeming with advanced intelligences operating on principles we don't understand, and we would never know. If we're early, among the first civilizations to arise, then of course we don't see anyone else. The universe is 13.8 billion years old, but Earth-like planets may have only become common a few billion years ago. Most intelligent life might be in the future, arising billions of years from now. But there's a darker interpretation, the anthropic shadow. We can only observe timelines where existential catastrophes haven't prevented our existence yet. If there's some universal catastrophe that wipes out technological civilizations, we wouldn't see evidence of others because they all got wiped out, and we're simply in the brief window before it hits us too. Maybe there's something about advanced technology that inevitably leads to extinction. AI, bioengineered pathogens, nuclear war, environmental collapse, or dangers we haven't imagined. If such a universal filter exists, then the galaxy might be full of extinct civilizations, and we're next. The Great Silence is not because intelligence is rare, but because it's doomed. Even if civilizations exist and persist, the vastness of space and light speed limits make interaction impossible. If intelligent civilizations exist millions of light years apart, communication is not meaningful. A signal takes millions of years to arrive, and by the time a reply returns, both civilizations have likely changed beyond recognition or gone extinct. The universe is structured to isolate intelligent life. Each civilization is trapped in its own light cone, perhaps able to detect ancient signals from others, but never able to communicate, share knowledge, or form relationships. We're all islands separated by oceans of space so vast that no bridge can cross them. This isolation worsens with cosmic expansion. The universe is expanding, and acceleration due to dark energy means distant galaxies are receding faster than light. Eventually, every galaxy will be isolated, alone in an expanding void, unable to see or contact any others. If we're alone, consciousness itself is extraordinarily rare and precious. We're not insignificant. We're incredibly significant, potentially the only consciousness in the observable universe, the only source of meaning and value in a cosmos that would otherwise be dead and meaningless. Without consciousness, the universe is just quantum fields in various configurations, obeying laws but not meaning anything. Consciousness creates value, transforms the raw physical universe into one with beauty, purpose, and understanding. If that perspective exists only here, then it's precious beyond measure. This places on us enormous responsibility. Every human being, every moment of experience, every act of creativity or kindness, these are cosmically significant because they contribute to the only pool of meaning that exists in the observable universe. When we risk extinction through war or environmental collapse or technological recklessness, we're threatening the only consciousness that exists. If we survive and flourish, our descendants could persist for billions of years, potentially experiencing and creating on scales we can barely imagine. The total amount of consciousness that could exist if we don't destroy ourselves is astronomical, and all that potential depends on what we do now, on whether we can reduce existential risks and preserve the one instance of consciousness we know exists. Some argue this reasoning is cosmic hubris, projecting our values onto an indifferent universe. The universe existed before consciousness and will exist after. From a detached perspective, our extinction would just be another event, like a star burning out. But value and meaning are inherently perspective dependent. They only exist from the inside, from conscious beings who care. And from that perspective, consciousness is special. It's the precondition for anything mattering at all. While the universe as a physical system doesn't care about consciousness, consciousness cares about itself. This creates existential meaning. We create meaning through what we care about and commit to. If we're alone, we're the only source of meaning, creating all value through our experiences and choices. This is profound responsibility, but also profound opportunity. We get to decide what matters, to create beauty and knowledge and love in a universe that would otherwise have none. We're not just building our future, we're building the only future. Every choice about managing existential risks, developing AI, preserving or creating consciousness, these aren't just local human questions, but questions about the ultimate fate of awareness in the universe. This should change how we think about priorities. Reducing existential risks becomes paramount, ensuring we survive the dangerous transition to advanced technology. All our political conflicts and economic concerns matter for present well-being, but they're secondary to whether consciousness persists. This doesn't mean single-minded focus on survival at the expense of everything else. That would undermine survival by making life not worth living, but we should be much more serious about long-term thinking, about coordinating globally to manage risks, about ensuring technological development is guided by wisdom, and we should cherish consciousness, appreciate the extraordinary improbability of awareness existing at all. Each moment of experience, each relationship, each instance of understanding or beauty, these might be the only such miracles in the universe. We are alone, but we don't have to stay alone. We might be the last ones, but we could be the first to spread consciousness beyond its origin world, the first to ensure its long-term survival, the first to answer why there's something rather than nothing by choosing to keep it going. If we survive and spread, we might eventually create or encounter other forms of consciousness, might seed intelligence throughout the cosmos. Billions of years from now, the universe could be full of awareness and meaning, rather than empty and dead, all tracing back to this moment, to this small planet where it all began. That's our challenge and our opportunity. We're the only intelligent life we know of, the only consciousness in the observable universe, the only hope that awareness and meaning will persist into the far future. Whether we succeed or fail depends entirely on us, on what we choose, on how we respond to the knowledge that we're alone. Let's choose wisely. Let's choose to continue. Let's choose to keep the light burning in the darkness, because right now we're the only light there is.